Hello, welcome to our integration series. Today we have a definite integral of square root of x times sine of pi times square root of x dx from 0 to 1. Now before diving in it, let me give you the idea of what I'm going to do and make a quick remark. From my experience, if you have an integral of the form of x to the n times sine of some constant times x dx, what we want to do is, using integration by parts, we want to take the polynomial function as u, so that we can later on differentiate it. The u will be n times x to the n minus 1, and the other trigonometric function, which is some sine or cosine, we can use it as a dv, so that then we can find an antiderivative and they will alternate, like sine will change into cosine and vice versa. So in the end, we will eventually get 1 from the polynomial, because applying differentiation n times, we'll get just 1. In this process, I just neglect the constants, but we should keep track of them in each step. The main point is that we want to, by polynomial I also mean it can be x to the n plus x to the n minus 1 plus some other terms, but we can always split such an integral into some smaller ones. So that's why I say polynomial, but it's actually x to the power of n. That is to say, you want to apply integration by parts, mainly to make one of these disappear, and in our case, x to the n is much more reliable option than trigonometric function. Now, I write all this so that you can understand the mechanics of these integrals, not to remember some rules or whatsoever. To understand the structure, each integral sometimes have different properties and requires different techniques to be solved, and they might vary a lot. Now we see square roots of x, and the one in the sine function makes things complicated, because we will have this function is a composite function of sine of x and square root of x. That's why it's not that trivial to find its antiderivative. Now, keeping in mind all these, the logical conclusion will be that we need to make a substitution, right? We make the substitution. We have y is equal to square root of x. Then, for the sake of convenience only, I want to square both sides. We can write x is equal to y square, right? And then compute dx. Dx in this case will be 2 times y dy. Also, we have some limits of the integral. We have x is equal to 0. In this case, well, since y is square root of x only, the y will be 0 as well. Let me mention it here, that again, y is equal to square root of x. The same for x equal to 1 and y is equal to 1, so limits won't change. Now let's rewrite the integral itself. Well, we have an integral from 0 to 1 of square root of x is y times sine of pi times y, and dx is 2 times y dy. Great. We can rewrite this expression as 2 times an integral from 0 to 1 of y squared sine of pi times y dy. Now we have the form we want to obtain. We have a sine function, and it's not a composite function. It depends only on y. Apart from this, we have the polynomial function. We have y squared, and our aim now will be to reduce this. Now all that remains is to be careful and do some technical things. Namely, we'll use integration by parts 2 times, I believe. And for the first time, let's write this in a clearer way. Alright, we have u as y squared, and then du will be 2 times y dy. Also we have dv, which is sine of pi times y dy. Now its antiderivative will be what? We definitely have, well, minus cosine of pi times y, and we need to, what, let's see, the derivative of minus cosine of pi times y is pi times sine of pi times y, so we need to divide this by pi. Now we can apply integration by parts, and as I did in my previous videos, let's write what we want to obtain from this. We want uv minus v times du, right? Alright, we have 2 times uv, it's minus y square over pi times sine of, cosine of pi times y, and we have limits from 0 to 1, minus an integral of from 0 to 1 again, du times v, right? And to not lose too much of a time, I propose writing plus here, since we have minus minus, like minus an integral of minus cosine, it will be plus eventually. Also, we have constants like 2 and 1 over pi, we can combine them, and then we are left with y times cosine of pi times y, right, dy. Great. Now all that remains is to compute this integral and also apply limits for this expression. Let's do so. It's 2 times, if you put 1, we will have minus 1 over pi times cosine of pi minus 1, well, 0 now. 0, yeah, it will disappear, so we only have minus 1 over pi times cosine of pi. Cosine of pi is minus 1, right? So we'll have just 1 over pi. Yeah, for this expression we have 1 over pi. It's 1 over pi plus we had 2 over pi, an integral of, we'll apply integration by parts one more time, and we'll follow the same idea that we have polynomial, we'll differentiate later on, and the trigonometric function, this time cosine of x, that we'll find an antiderivative of. This time I don't want to dive into notation of u and v, dv, to save some time and space. I think we are capable of doing this integral in our head, so let's try. The y is the function that we'll differentiate later on, so first we need to find an antiderivative of cosine of pi times y. Y stays the same, we have antiderivative of cosine of pi times y, it's sine of pi times y over pi, right? Quickly differentiating this, we obtain this, so everything is fine. Now minus, we just repeat, I forgot limits here, minus, again, we just repeat the antiderivative we obtained earlier on, it's sine of pi times y over pi, and we differentiate this function, it's y, its derivative will be just dy, like 1 times dy. So we have just dy here, right? I hope that's clear. Nevertheless, if you have some questions, please write them. Now we have, let's open up the brackets. We have 2 over pi plus 4 over pi, and now we can open up the brackets again. I must multiply this, and this expression remains. Let's apply boundaries again. We have, for the lower boundary, we have 0 as before, so I won't write this, like minus 0 it will be. For an upper one, we have 1 over pi times sine of pi over pi. Sine of pi was 0 as far as I remember, so we have 0 for this expression, so it's just 0. Alright, then we are left with our integral, last integral hopefully that we have. It's minus 1 over pi, an integral of from 0 to 1 of sine of pi y times dy, which is an obvious one. So, not losing time, I write 2 over pi plus, well, minus 4 over pi square, and an integral, this integral it will be what? Minus cosine of pi times y over pi, right? And it's from 0 to 1. Let's write it in a more neat way, which is 2 over pi plus 4 over pi cube of cosine of pi times y from 0 to 1. Right? Now quickly computing this, we have like cosine of pi minus cosine of 0. Now this is minus 1, this is 1, right? So we have minus 1, it's minus 2. And we write this to our expression, final one. We have 2 over pi plus 4 over pi cubed times minus 2, right? And it's 2 over pi minus, well, 8 over pi cube. Now this is our final answer. I'll leave it like this. I think it's enough as a final answer. Here it is. The quick review of what we did is the following. I gave an idea, then we make the substitution to have a form we want to obtain, and after this part, as I said earlier, and as you saw, everything was technical. Just being accurate, attentive, and evaluating integral by integration by parts. I hope you got the idea of the internal logic of these integrals, and it's not like you just remember some rules or whatever. In the end, we have a nice answer. We didn't use our back substitution because it was a definite integral. Yeah, here it is. If you have some further questions, you are very free to write them in the comment section. And see you on the next videos. Bye.